Oh shit. What the fuck? A few months ago, I got like $10,000 worth of gearboxes and motors for like a robotics competition I was supposed to do. And the robotics competition's in a month now, and I've been like omega procrastinating. I haven't built anything yet. I haven't even designed anything yet. Yeah, you know what? I'll get started. Alright, let's see what we got in here. Yo, these motors look hella expensive. Alright, so I'm gonna combine this motor, which is like something like $500. Bro, they pack these like freaking those Lay's potato chip bags. It's 90% air in here. I got one of these guys that Harmonic Drive sent me. Yeah, when you spin this guy, it goes. The issue is these objects aren't designed to be compatible with each other. So now I have to like machine something funky to, you know, have them go. Yeah, light work. Okay, so I'm gonna have to machine two things for this gearbox. The first is a mounting plate. So this mounting plate will allow this motor to attach to the interface with this and be totally centered. All right, it's done. To build an actuator, you're actually gonna need more than just the gearbox and the motor and have them coupled together. You need something to control it. So, of course you need the gearbox. And of course you also need the motor, but you also need a motor controller. So I'm using the Modius R411, which is a FOC driver for robotics specifically. So this thing is like pretty smart and will be able to do all the robotics nonsense that I need it to do. It has a magnetic encoder here. So what I need to do is take the motor and put a magnet here later on as well. The three things you need to build a robotic actuator: motor, controller, and gearbox. Magnet, controller, and a housing. This is a lot of plastic, but literally all it does is hold the controller in place. You need to have the magnet be perfectly aligned with the magnetic encoder on the FOC driver or the speed controller. The next thing I'll need is I need a shaft that I machined to adapt the shaft of this motor to the shaft of the gearbox. This is a 14mm diameter here, and this is only a 10mm shaft. So I'm going to machine this piece of aluminum, which has a 14mm outer diameter and a 10mm inner diameter. So let's go ahead and do that. I had to machine this shaft 3 times. The first clip, you might have noticed that I was using calipers to measure the outer diameter. And calipers are like usually pretty good, but when you need perfect press fits, they don't cut it. So I machined it, didn't get a perfect press fit, and had to redo it again. I learned my lesson and used one of these guys. It's a more precise measurement instrument called a micrometer. You can put it around here and then rotate this knob and it clicks once it's hit its max torque. And you can see I was looking for 14mm. I got 13.884 millimeters, way too off. So I had to machine it again. That's why in the next clip you'll see me using one of these guys to measure while I'm machining the part. What is this? Do you guys see that? This shit vibrating like crazy. When that happens, you get shafts that aren't concentric at all. So like, bro, this is ass. This is literally unusable. So I had to remake this one more time, measuring with the micrometer and drilling it not poorly. So the reason that happened is because I forgot to center drill, which you do a little ponk into the material and that centers everything. But it's also really hard to get centering done with just a lathe and a drill bit. The correct way to do it is use a boring bar, but I didn't have one on hand either. Okay, so here I also do something kind of stupid. I want to screw in these 4 holes, right? So here, let me do a section view here. This is the head of one of the screws, and you can see there's barely enough room for it to not touch the side of the motor, but it's like really close, and it just about touches the side of the motor anyways. This is like, so I went ahead and just machined down the head of the screw instead. Okay, an important thing to note is that these motors were designed for some sort of connection that I don't have, some sort of like industrial grade motor controller. Since I'm using a Modius motor controller, which is closer to like something for hobbyists, I kind of just have to jump the pins back here. This is a 3-phase motor, which means I only care about 3 of the pins here, and the rest of the pin is just like ground and Hall effect sensors. So I just look at the data sheet and figure out what pins I need and hard solder directly to those pins. Okay, after building an actuator, you usually need a computer to run it. So here I'm using a Raspberry Pi to control it, and this is a CAN-FD hat. So when you build robotic actuators, there's protocols that you care about, like RS-45, CAN, and CAN-FD. CAN-FD is like one of the more up-to-date communication protocols that you'll see in robotics. So this pretty much allows the Raspberry Pi to translate signals into CAN-FD, which is the information that the information that this cares about to run it. So effectively this, when you combine the two together, the Raspberry Pi tells the Modius controller, hey, go to this position. And this will do some fancy code and make the motor go to a certain position. But setting one of these up and controlling it is kind of a pain. I'll have a nice document in the description for you to read through. And then afterwards, you need to go through and wire everything up. So this is the communication line, so CAN-FD line goes here, and then this is a terminating resistor. When you do CAN-FD, you need to have a terminating resistor to tell you you're at the end of the line. Because normally there's 2 ports here. One is information in and then information out, so you can chain together multiple of these boards so that you can control multiple motors. If you're at the end of a chain, then you want to have a termination resistor in one of the lines. I only have a chain of 1, so terminate it immediately. Oh, fuck. Guys, if you run it back and look right around here, you'll see some freaking magic smoke happen. It was at that point where I was like, dude, I'm totally cooked. I burned out a $600 motor. I only have 6 of these motors, so if I burn out one, I can't build a 6 degree of freedom robot arm anymore. So it's literally so Jover if it breaks. It started smoking. A little bit of magic smoke. Fuck. Guys, I'm kind of stupid. So I was jumping the phases of this because this is designed for a different type of controller, which I don't have. And I started it, it's supposed to be 4, 7, and 8. And I started it like wrong, but it feels normal. So hopefully we didn't like Omega cook the motor. Because if we Omega cook the motor, bro, that's like $600 down the drain. This motor's really expensive. Still smells like magic smoke though. And honestly, it totally smells like it's coming from the motor, bro. Time to do some resoldering. Okay, let's try again. Okay, these are good noises. Oh, it's spinning. Let's go. I didn't cook the motor. Dude, I totally thought it was $700 down the drain. So I have all the code going. When I press enter, hopefully it works and I can control it with this controller here and the motor doesn't fry itself. Alright, well, it errored out. Okay, now it should work. Okay, no it doesn't. Okay, this should work. Oh! Yo, it works! Do you know what the easiest way to calculate torque is? Say I have a motor here. I want to calculate how much torque this guy can do. All you gotta do, connect up a stick, have a scale here, rotate it down, and then see what the scale says. Because torque is distance times force. And if you know force from the scale, and you know distance because you're the guy that counted the stick, then you know torque. So let's go make that stick. Okay, I'm seeing like 2-ish kilograms. I think that's good. Alright, what does 2 kilograms of force on that scale actually tell us? and we get 4 Newton meters of torque. That's fucking shit. Especially for a gearbox, a freaking massive gearbox. I'm so scared to increase the current further because I've already tried it once, and like, this is a $600 motor. So, alright, this is with a current limit of 10. Oh shit. Oh, what the fuck? My bad. Oh my god. Holy shit. Yeah, I half expected that to happen, and I was like, yeah, it'd be cool if it explodes for content. But I actually also, after the couple of first initial tests, I didn't actually think it was gonna break. But I did 3D print a stronger version. Okay, I've set it to 20 amps now. This is the one I'm most scared about, to be honest. 20 Newton meters. The motor and the motor controller aren't warm, so I can keep increasing. Okay, this is 30 amps. Oh my god. I guess my clamping setup's pretty bad. Since the datasheet says the stall current is 30 amps, then I'll listen to it and keep the current limit at 30 amps. Oh shit. No! It bent some pins. I'm pretty satisfied with the amount of torque that I get, so. Alright gang, that was 1 motor down, 5 more to go, and I have to build the rest of the freaking robot arm. There is 16 days until competition, and only 1 gearbox done. So wish me luck, guys. Oh, and like and subscribe to keep up to date.